in the infinite darkness between the stars, where light travels unbroken for billions of kilometers before touching anything at all, there drifted a solitary traveler, silent, cold, unremarkable at first glance. It was a stone of emerald fractures, spinning slowly through the void. Its surface was jagged yet smooth in places, etched with scars that hinted at a long, violent journey. 3 impacts had struck it in succession, each collision that should have shattered it, that should have rendered it inert, leaving only debris in the silent blackness. Yet it endured. Not merely endured, it changed. A subtle glow pulsed from its fractures, a trembling, ethereal light that seemed almost deliberate, almost sentient. How could something so ancient, forged in the chaos of interstellar space, so silent and so still for countless millennia, react? How could an object, mere rock and metal, exhibit what might be called awareness? The paradox lingered in the minds of those observing from Earth, a mechanical body behaving as if it had a consciousness. It was a question that unsettled the boundaries of physics, of chemistry, and perhaps of philosophy itself. The 3 strikes had been violent and unforgiving. Micrometeoroids, fragments from distant collisions, had battered it, each strike leaving jagged scars across its surface. The first should have sent it tumbling uncontrollably, its momentum disrupted. The second should have fragmented it into a cloud of debris. The third, arriving with a sudden, almost cruel precision, should have ended its existence entirely. And yet, after the final impact, something deep within the object seemed to awaken. Tiny veins of green light flickered across its body, as if energy, long dormant, had suddenly stirred. Its rotations subtly shifted, no longer random, but deliberate. A hint of a pattern beyond immediate comprehension, subscribed now to witness the universe's secrets unfold, and follow the story of 3i, Atlas, as it challenges everything we thought we knew about space telescopes. Across the world detected these anomalies. Electromagnetic readings pulsed in irregular sequences, sometimes mirroring the chaotic rhythm of cosmic radiation, and sometimes with unnerving regularity, like a heartbeat emerging from stone. Astronomers, initially dismissive, began to whisper among themselves, uncertain yet compelled by the evidence. This was no longer merely a celestial object drifting through space. It was behaving like a response. The universe, or at least this fragment of it, had begun to react to its environment in ways that mirrored awareness, intention, or something approaching them. And within that glow lay the philosophical weight of the moment. What if the universe is not entirely mechanical? What if, in the fabric of matter itself, in the collisions of atoms and the fractures of crystalline lattice, there lies the potential for intelligence? Not biology, not life as we understand it, but a form of sentience emerging in the unlikeliest of vessels. Here, in the cold silence of interstellar space, humanity glimpsed a possibility that defied the conventions of understanding. 3i, Atlas, as it had been catalogued, had become more than an object. It had become a question, a phenomenon that challenged perception, a reminder that the cosmos could be more alive, more reactive, more mysterious than any observer could imagine. And as it continued its drift through the void, pulsing faintly, the observers on Earth waited, captivated, aware that this was only the beginning. This was the awakening after the initial detection of 3i Atlas. Astronomers traced its path with growing fascination. Between 2020 and 2025, ground-based observatories and orbital instruments followed the object across the solar system, each observation adding nuance to a story that seemed almost alive. Unlike its predecessors, 1i Oumuamua and 2i Borisov, which had passed largely without fanfare, 3i Atlas did not simply drift. Its rotation was irregular, fluctuating in ways that defied simple gravitational modeling. Tiny corrections in its trajectory hinted at subtle forces at play, forces that were neither fully understood nor easily explained. Data from Pan-STARRS captured the first anomalies, noting deviations in spin and brightness inconsistent with an inert rock. Hubble's precise instruments revealed that its fractured surface reflected light unevenly, with glimmers of unexpected wavelengths, while ESA's Gaia telescope recorded minute trajectory shifts, suggesting an external or internal influence. Nothing in the mechanics of classical physics accounted for these variations. Each observation seemed to whisper the possibility that 3I Atlas was responding not randomly but with purpose. However faint after the first impact, astronomers observed a sudden, faint green pulse emanating from the object, a non-thermal emission that did not align with solar reflection or background radiation. The second strike produced a similar phenomenon, slightly stronger, its pattern more pronounced. When a cluster of micrometeoroids intersected the object's orbit near Mars, delivering what became known as the third strike, the reaction was unmistakable. The stone pulsed with energy, a subtle shimmer across fractured surfaces, as if the collision had awakened a dormant mechanism. Instruments detected energy absorption ratios that contradicted prior models, suggesting the object was not merely absorbing energy, but transforming it, releasing it in deliberate bursts. Astronomers described the moments with hushed awe. Observers in observatories across the globe leaned closer to monitors, adjusting filters and recalibrating instruments, unsure whether they were witnessing a natural phenomenon or something unprecedented. The excitement was tinged with unease. The data suggested an object that was not only moving through space, but reacting to it. The subtle shifts, the glowing pulses, and the anomalies in rotational mechanics all pointed to one unsettling possibility. 3I Atlas was awake in some sense, its behavior more than the product of inert matter. The realization carried philosophical weight. If the motion was not propulsion, and the signals were not coincidence, then what guided it? Could matter itself, in the right conditions, develop an emergent responsiveness? Could the collisions, 3 strikes in succession, have been the catalyst for a form of awareness, a spark ignited by the forces of the cosmos? The answer remained unknown, but the evidence was undeniable. Something had shifted within 3I Atlas, something that challenged the very assumptions of observation and control. The universe, in its vast silence, had produced a voice, subtle yet perceptible, in the pulses and deviations of a solitary interstellar traveler. As 3I Atlas continued its journey through the solar system, its motion began to defy expectations once more. Small yet consistent deviations from its projected path toward the inner planets caught the attention of orbital analysts. Each adjustment was subtle, barely measurable in conventional terms, yet when traced over time, the trajectory suggested intent. The object's path was bending slightly, an almost imperceptible turn toward Mars that could not be explained by gravitational influences alone. Scientists debated whether this was a result of internal forces, momentum released from structural adjustments, microfractures reacting to impacts, or energy stored and released in ways previously unobserved in interstellar objects. Each possibility opened new questions about the physics governing matter in extreme isolated conditions. SPECTROSCOPIC Studies revealed anomalies in composition that further deepened the mystery. Analysis of reflected light and absorption patterns indicated crystalline structures far more complex than anything encountered on Earth. Some compounds appeared to be exotic silicates and metallic alloys, yet with lattice configurations unknown to terrestrial chemistry. These structures suggested that the object's internal composition could interact with energy in unconventional ways, storing it, channeling it, and releasing it intermittently. Such material properties, while theoretically possible under extreme interstellar pressures and cosmic radiation exposure, had no precedent in observational astronomy. The evidence pointed to a natural origin, yet the behavior hinted at something beyond simple mechanics. Even more compelling were the periodic emissions of light, observed along the fractures and surface ridges. Careful measurement revealed sequences following mathematical ratios closely approximating Fibonacci patterns. In nature, such sequences appear in biological growth and self-organizing systems. Yet, on a lifeless rock, their presence was perplexing. These pulses were not constant or random. They appeared in intervals that could be predicted with surprising precision, indicating an underlying structure or process. While scientists cautioned against anthropomorphizing, the regularity suggested a mechanism operating with a degree of internal coherence and internal response to the collisions and environmental stimuli. The anomaly quickly attracted public attention. Leaks from ESA and NASA's Jet Propulsion Laboratory spread across news networks worldwide. Media outlets dubbed the object the Green Eye of Mars, reflecting the pulsating green light seen in telescope imagery and the growing fear that the object's trajectory toward the red planet was no accident. The public reaction was immediate, mixing wonder with apprehension. Images of the object, captured from multiple observatories, circulated online, sparking debate over whether humanity was witnessing a natural phenomenon or the first signs of something not entirely inert. Amid the fascination, an undercurrent of unease spread through the scientific community. There was excitement, yes, for discovery, but also a quiet tension born of the realization that the universe could present behaviors entirely outside established frameworks. For centuries, humans had measured, modeled, and predicted the motion of celestial bodies. Now, an interstellar traveler challenged that assumption. It moved with a subtlety that suggested reaction, almost awareness, and in doing so, confronted humanity with the limits of understanding. The very act of observation became fraught with ethical and philosophical weight. Could observing and tracking an object of unknown capabilities trigger unforeseen consequences? The deeper the data were examined, the more apparent it became that conventional physics could not fully account for the phenomena. The trajectory, the energy emissions, the internal material composition, and the patterned pulses all indicated that 3I Atlas was more than a rock. It was a singular presence in space, behaving in ways that blurred the line between inert matter and responsive system. Each observation raised the stakes, emphasizing that this was no longer a passive event, but a mystery that demanded contextual understanding. To understand what 3I Atlas truly represented, to grasp the origin of its anomalous behaviors and the forces shaping its movement, scientists knew they had to look beyond the solar system. Its story did not begin with its detection. It began far away in the deep reaches of interstellar space, long before it entered the familiar gravitational embrace of the planets. The answer, elusive and complex, required tracing its path backward, unraveling billions of years of cosmic history, and confronting questions that might redefine humanity's understanding of what constitutes matter, energy, and perhaps even consciousness itself. Analysis of 3I Atlas's trajectory indicated that its acceleration anomalies were not uniform across its surface. Using high-resolution imaging combined with orbital simulations, scientists determined that certain regions of the object appeared to contribute disproportionately to changes in momentum. These areas corresponded to large fractures and exposed crystalline structures, suggesting that the internal mass distribution and material composition were uneven and potentially dynamic. Researchers proposed that structural rearrangements within the lattice could produce small thrusts, consistent with observed deviations. Though such mechanisms had never been recorded in naturally occurring interstellar objects, spectral data collected over multiple observation periods provided further insight into the object's composition. Elements such as iron, nickel, and silicate compounds were present, but they were integrated into crystalline networks unlike any known terrestrial mineral. Laboratory simulations attempting to replicate these lattices under high pressure and low temperature conditions demonstrated unusual properties, including the capacity to store and release electromagnetic energy. The consistency of these responses across repeated impacts suggested that the object's internal structure functioned in a way that allowed it to redistribute energy from external forces, potentially contributing to the observed acceleration changes. Electromagnetic monitoring revealed that the green pulses were not random. Their timing and sequence could be statistically mapped and predicted with a high degree of accuracy. While the absolute energy output of each pulse was modest, the structured nature of the emissions indicated an organized process rather than chaotic release. Scientists proposed that these signals could be the result of microfractures propagating through a lattice, capable of piezoelectric-like responses. Alternative hypotheses included quantum tunneling effects within the crystalline structure or transient plasma channels formed during impact events. Each explanation, however, required assumptions about material properties not yet fully understood or observed outside laboratory conditions. Observational teams coordinated to cross-validate data from multiple instruments, optical telescopes, infrared arrays, and radio sensors all contributed complementary measurements, confirming that the anomalies were intrinsic to the object and not artifacts of instrumentation. The repeated detection of trajectory adjustments, energy emissions, and spectral irregularities established a pattern that was scientifically verifiable. It was increasingly clear that 3I Atlas could not be classified alongside previously observed interstellar objects, and its behavior required the development of new models in celestial mechanics and material physics. The dissemination of these findings generated intense interest within the global scientific community. Conferences and collaborative working groups formed to analyze the object's properties in detail. Preliminary papers outlined potential mechanisms for internal energy redistribution and self-correcting motion, while cautioning that no current theory could fully account for the combination of observed phenomena. Ethical discussions also emerged, centered on the implications of studying an object exhibiting responsive behavior. The possibility that continued observation could trigger further reactions was raised. Though there was no evidence to suggest the object was consciously aware in any traditional sense, the combination of acceleration anomalies, exotic material composition, and structured emissions positioned 3I Atlas as an unprecedented scientific subject. Its motion toward Mars, while subtle, remained a focal point for further monitoring. Each additional observation reinforced the conclusion that 3I Atlas was a distinct class of interstellar object, one that challenged established assumptions in astrophysics, planetary science, and material chemistry. The evidence indicated that its anomalous properties were inherent and reproducible, making it a unique, natural experiment on a scale and in an environment inaccessible on Earth. The journey to understand 3I Atlas required tracing its path backward through the void, reconstructing a trajectory that spanned light years and centuries. Using high-precision astrometric data, scientists applied reverse orbital modeling to estimate its point of origin beyond the confines of the solar system. Early simulations suggested a path originating somewhere in the vicinity of the Lyra constellation, or possibly Vega. though the immense distances and the influence of interstellar forces made exact determination impossible. Even minor gravitational interactions with unseen masses along the way could have altered its course. Yet the models consistently indicated that 3-1 Atlas had traveled a vast and largely uninterrupted journey from a distant stellar neighborhood. Comparisons with prior interstellar objects underscored the anomaly of 3I Atlas. 1I Oumuamua had entered the solar system at high velocity, exhibiting unusual elongation and minor non-gravitational acceleration, yet it remained inert, a passive visitor. 2I Borisov, a comet from another star system, displayed familiar cometary activity, but no internal complexity beyond sublimation. 3I Atlas, by contrast, was distinct. Its trajectory adjustments, energy emissions, and structured responses to impacts marked it as fundamentally different. It was not merely an interstellar traveler. It was an object whose behavior suggested interaction with its environment, hinting at internal processes that other objects had never displayed. Beyond the physics, there was a profound philosophical weight to its voyage. Interstellar space, often thought of as empty, is, in fact, a vast graveyard of matter, remnants of stars long extinguished, fragments of planets broken by collisions, and debris from processes that predate the formation of our own solar system. 3I Atlas could be considered part of this cosmic memory, a fragment carrying within its structure the history of countless events and forces. Its material might hold evidence of conditions in distant star systems, of chemical processes that have occurred nowhere else, or even, in a more speculative sense, traces of organized structures that evolved in isolation for millions of years. The object became a silent witness to the history of the galaxy, a tangible reminder that matter itself can carry the record of time and transformation. The arrival of such an object underscored a startling realization. The solar system is not isolated. Far from being a static, self-contained environment, it is a crossing point, a temporary intersection in the paths of objects that have traveled vast interstellar distances. Humanity, once confident in its understanding of local celestial mechanics, now faced evidence that the solar system is periodically visited by objects with unknown origin, composition, and behavior. Each visitor challenges assumptions about isolation, predictability, and the scale of cosmic interactions. Astrophysical theories began to emerge to explain the possible origins of the observed behavior. High-energy, cosmic radiation, prolonged exposure to interstellar particle flux, or repeated microcollisions could have altered the crystalline lattice of 3I Atlas, producing structural defects capable of energy storage and release. Quantum mechanical effects, though speculative, offered another pathway for emergent reactivity, as defects or asymmetries in crystal formation could generate measurable electromagnetic anomalies. While no single theory fully accounted for all observed phenomena, the combination of known interstellar forces and unusual material properties provided a plausible framework for understanding how such an object could develop responsiveness over vast timescales. Yet even with a probable origin and plausible mechanisms, one question remained unresolved: the internal behavior. Tracing its path, identifying potential sources of its material, and understanding the forces acting upon it revealed context, but did not explain the patterns of energy emission, the trajectory corrections, or the structured pulses that had first signaled its anomaly. The external journey was now understood. The internal processes remained a mystery. To comprehend 3I Atlas fully, it was necessary to look deeper, to explore what lay within its fractured and enigmatic form. and to confront the implications of a system capable of reacting to the universe around it. Further examination of 3I atlases path required integrating data from multiple observation platforms over several years. By combining positional data from Pan-STARRS, Hubble, and ESA's Gaia telescope, scientists were able to reconstruct a three-dimensional model of its trajectory with high temporal resolution. The models suggested that the object had entered the solar system at an unusually low inclination relative to the ecliptic, which is rare for interstellar objects. This implied that its approach was neither random nor typical of the majority of bodies passing through the galaxy, suggesting that 3I Atlas had avoided significant perturbations from stellar or planetary encounters during its journey, maintaining a relatively coherent path for millions of years. Comparative studies with 1I Oumuamua and 2I Borisov emphasized 3I Atlas's uniqueness, whereas Oumuamua displayed extreme elongation and slight non-gravitational acceleration. It lacked structured emissions or evidence of energy reactivity. Borisov, a cometary body, exhibited predictable outgassing, but no anomalies beyond conventional cometary physics. 3I Atlas, in contrast, combined multiple unusual features: irregular rotation, electromagnetic pulses following structured sequences, and acceleration deviations correlated with impacts. This combination could not be explained by known cometary or behavior and suggested internal processes not previously observed in interstellar objects. Astrophysical modeling of its material composition provided further insight. Laboratory simulations of exotic crystalline lattice indicated that prolonged exposure to cosmic radiation and micrometeor bombardment could induce lattice defects, capable of storing mechanical or electromagnetic energy. These defects, when subjected to sudden external stress, could release energy in controlled bursts. Such a mechanism would explain the observed pulses following impact events and could account for minor trajectory adjustments, though the degree of coordination suggested by the Fibonacci-like sequences remained difficult to reconcile with purely physical processes. Quantum-scale phenomena, including tunneling effects and localized charge accumulation, were proposed as potential contributors to these behaviors, but no definitive evidence currently exists. The interstellar environment itself likely played a significant role in the development of 3I Atlas's properties. Traveling through regions of variable radiation density, interstellar magnetic fields, and particle flux over millions of years could have contributed to structural and chemical evolution in ways that are not replicable on Earth. Modeling indicated that repeated exposure to high-energy cosmic rays can alter crystalline structures at microscopic scales, introducing asymmetries and defects that may produce emergent reactivity. Combined with sporadic collisions and pressure changes, these processes could create conditions for measurable electromagnetic responses and limited self-adjustment of motion. The broader implications for astrophysics and planetary science became increasingly apparent. Interstellar objects, like 3I Atlas, are not merely passive debris. They are carriers of extreme histories and environmental conditioning. Their trajectories, compositions, and behaviors provide indirect records of conditions far beyond the solar system. Studying these objects allows scientists to test models of material response under long-term cosmic exposure, and to refine theories of interstellar chemistry and physics. In the case of 3I Atlas, the presence of structured energy, emissions, and acceleration anomalies suggested that such long-term processes can produce behaviors previously considered impossible for inert matter. While the origin and travel path of 3I Atlas were now reasonably well understood, The internal mechanisms producing its unusual behavior remained unexplained. The scientific focus was shifting from external trajectory and material composition toward direct inference about internal structure and energy dynamics. This transition marked a critical turning point. Understanding where the object came from could contextualize its journey, but comprehending what it contained and how it responded to external forces would require new methods, models, and possibly a re-evaluation of assumptions about the behavior of interstellar matter. As the anomalies of 3I Atlas became undeniable, the scientific community found itself divided. Observatories and research institutions across the globe debated the next steps, some advocating for continuous monitoring and experimental probing, while others warned of the dangers of interfering with an object whose behavior could not be predicted. The first camp argued that every data point was essential, that understanding this object could redefine physics, materials, science, and interstellar dynamics. The second camp countered that humanity had no framework to anticipate consequences, and that even subtle experiments might provoke reactions beyond comprehension. The division was sharp, with meetings and conferences reflecting both the intellectual thrill and the existential anxiety of the moment. Political agencies soon took notice. Behind closed doors, committees were formed to assess the potential risks. The secrecy of these groups mirrored historical debates surrounding SETI, when scientists and policymakers considered whether to respond to potential extraterrestrial signals, and Cold War protocols regarding unidentified objects near strategic zones. Questions of national security and global safety became entangled with scientific curiosity. Every proposal to study or interact with 3I Atlas was weighed against the possibility of unintended consequences, forcing governments to navigate between transparency and caution. Public disclosure had already occurred in limited form, but much of the planning happened out of sight. In briefings, classified reports, and encrypted communications. Amid the institutional tension, the ethical dimension emerged as a central concern. Humanity's paradoxical relationship with the unknown was on full display. Curiosity demanded that the object be observed, tested, and understood. Fear counseled restraint, reminding everyone that the object was fundamentally alien, possibly reactive in ways undetectable until too late. The question lingered: did the right to knowledge outweigh the right to caution? Was it ethical to manipulate or study an object if it possessed, even minimally, a form of intelligence or reactivity? Scientists confronted the uncomfortable possibility that every decision carried moral weight, extending beyond traditional risk assessment to a consideration of consent, awareness, and the unknown capacities of the object itself. Within this context, personal experiences became as compelling as the data itself. Among the researchers was a composite figure, representing the human side of this scientific reckoning. He spent nights monitoring live feeds from space telescopes, the faint green pulses of 3I Atlas casting an unnatural glow across his workspace. Sleep became intermittent, interrupted by simulations, calculations, and the repetitive loops of trajectory reconstructions. He felt the weight of responsibility, the tension between duty and dread, as if the object were watching in return. In his reflections, he acknowledged the thrill of discovery, while recognizing a creeping unease. Every new data point was also a reminder of the unknown, of the possibility that the universe had introduced something humanity was not prepared to encounter. The ethical stakes became unavoidable. The scientific community asked not only what the object was, but what humanity was permitted to do. If 3I Atlas exhibited even rudimentary responsiveness, did probing its structure constitute interference with a nascent form of awareness? Could experiments be justified on the grounds of knowledge, or did the possibility of provoking harm demand restraint? These questions, theoretical yet urgent, became central to every meeting, every simulation, and every observation strategy. Despite the fear, curiosity prevailed. The human instinct to investigate, to measure, to understand, proved stronger than caution. Scientific instruments were readied, protocols refined, and observation campaigns expanded. The world collectively held its breath as the next phase of study began. The decision was clear. Even if the implications were not, the only way to know the truth about 3I Atlas was to look closer. And so they did, preparing to probe not just the object's trajectory or surface, but the very processes that seemed to make it unlike anything humanity had ever encountered. The first phase of intensified observation involved coordinated campaigns across multiple observatories worldwide. Optical telescopes, radio arrays, and infrared detectors were synchronized to capture continuous data on 3I Atlas. Each instrument focused on different parameters: rotational variations, energy emissions, spectral signatures, and minor trajectory deviations. The aim was to compile a comprehensive data set that could reveal internal mechanisms or behaviors not previously observable. Teams worked in shifts to maintain near-constant monitoring, aware that even brief lapses could miss critical events, particularly as the object continued to approach the inner solar system. Simultaneously, computational models were updated to incorporate all available data. High-resolution simulations accounted for gravitational influences from Mars, Earth, and the asteroid belt, as well as solar radiation pressure and interstellar particle flux. These models were cross-referenced with live observations to detect inconsistencies and anomalies. Early results reinforced the initial concerns. 3I Atlas continued to display acceleration changes that could not be fully explained by conventional physics. The anomalies were small but consistent, providing additional evidence that some internal or structural mechanism was contributing to its motion. The scientific debate intensified as new results were analyzed. Half of the research teams advocated for deploying active probes or directed observational experiments, such as high-intensity light pulses or low-energy impact tests, to understand the object's responsiveness. They argued that such interventions were essential for characterizing its properties, including potential energy storage and electromagnetic behavior. The other half of the community maintained that any interference could provoke unknown reactions, emphasizing that the object's structured emissions suggested sensitivity to external stimuli. This disagreement extended to international scientific bodies, complicating decision-making and slowing coordinated action in parallel. Ethical committees reviewed the implications of direct experimentation. Legal and philosophical advisors questioned whether humanity had the authority to manipulate an object that might exhibit emergent responsiveness. Scenarios were modeled for potential outcomes, including structural fragmentation, unpredictable energy discharges, or accelerated changes in trajectory. While the likelihood of catastrophic consequences was assessed as low, the uncertainty remained, and every decision carried both scientific and moral weight. The debates mirrored those faced during early SETI discussions, when the question of contacting extraterrestrial civilizations prompted discussions about global consensus and the precautionary principle, individual. Scientists began experiencing the psychological impact of constant observation. Extended monitoring of live feeds, coupled with the pressure of high-stakes analysis, created stress and fatigue. Researchers reported difficulty concentrating, sleep disruption, and persistent preoccupation with the object's behavior. For many, the glow of 3I Atlas's pulses became more than a data point. It was a visual reminder of the unknown, a manifestation of uncertainty that compounded both curiosity and anxiety. Some team members expressed concern about the broader implications for humanity, questioning whether observing and potentially provoking a reactive object was morally justifiable. Despite these concerns, preparation for controlled experimental observation advanced. Communication protocols were established to coordinate responses across international research teams. Redundant monitoring systems were installed to ensure real-time tracking, and simulations were used to predict the effects of low-energy interactions. The consensus, tacit if not universal, was that careful observation with controlled interventions represented the only viable path forward. The object's approach, its acceleration anomalies, and its internal energy behaviors demanded closer study, even in the face of uncertainty. By the end of this phase, the scientific and ethical framework for investigation was in place. Observation schedules, simulation protocols, and decision-making hierarchies had been defined. The teams were prepared to collect unprecedented data while simultaneously managing the moral and practical risks. The tension between fear and curiosity had not been resolved, but it had been formalized into a structured approach. Humanity would proceed cautiously, systematically, and deliberately. The next steps promised not only to reveal the mechanics of 3i Atlas, but to test the limits of human understanding in the face of an object unlike any previously encountered. As 3.1 Atlas drew closer to the inner solar system, observation alone was no longer sufficient. NASA and ESA deployed a series of autonomous probes designed to approach the object at safe distances while performing high-resolution spectrometry, magnetometry, and thermal scanning. The probes, engineered to withstand the radiation and micrometeoroid environment near Mars' orbit, were tasked with collecting unprecedented detail about the object's surface, internal structure, and electromagnetic behavior. Teams on Earth coordinated their trajectories and observational windows with precision, aware that even minor miscalculations could compromise the mission. Footage relayed from the probes revealed details that defied conventional expectations. The surface of 3i Atlas was fractured and irregular, yet it glowed with a persistent green luminescence, concentrated along microfractures and fissures. Geometric pulse waves rippled across the surface in response to both minor collisions and ambient electromagnetic fluctuations. Inside the stone, sensors detected faint plasma channels threading through crystalline lattice, forming interconnected networks resembling capillaries. The visual data suggested a material complexity that blurred the line between geology and engineered structure, and scientists struggled to reconcile these patterns with known astrophysical or chemical processes. Unexpectedly, the probes began to experience interference that could not be explained by equipment failure or cosmic noise. Instruments fluctuated, readings oscillated without correlation to external conditions, and subtle forces appeared to resist the probe's approach. Magnetic and electric sensors detected transient fields that seemed to interact directly with probe electronics, as though the object itself were influencing them. Analysts described the effect as pushing back, not in a macroscopic mechanical sense, but as a disruption of measurement signals. Multiple teams cross-validated their instruments, confirming that the anomalies were genuine, consistent across devices, and localized to the immediate vicinity of 3i Atlas. Among the most startling findings was a series of thermal fluctuations captured by one probe. Sensors recorded rhythmic variations across multiple sites within the object, following a repeated, structured pattern. The cadence resembled neural firing sequences, with energy pulses propagating along the crystalline channels in a manner reminiscent of self-organizing systems. While the exact mechanism was unknown, scientists suggested parallels with theories of emergent quantum-level coherence. similar to concepts proposed by Penrose and Hameroff regarding consciousness arising from microtubular structures. While there was no evidence of cognition, the data implied internal coordination within the object that responded predictably to external stimuli. The probe's recordings also revealed secondary electromagnetic emissions timed with surface vibrations. Minor impacts or radiation fluctuations triggered complex responses in both the plasma channels and crystalline lattice. These observations indicated that 3I Atlas possessed a form of internal energy regulation, absorbing external forces and converting them into structured outputs. The effect resembled a form of feedback, an internal system capable of responding to perturbations with measurable consequences in its motion, emissions, and internal energy distribution. The cumulative evidence suggested that humanity had encountered a phenomenon unlike any known interstellar object. While not biological in the conventional sense, 3.1 Atlas displayed behaviors consistent with responsiveness and self-organization, challenging definitions of life, agency, and consciousness. Researchers realized they had reached the limits of observational certainty. They were no longer dealing solely with an inert rock, but with a system that could interact, respond, and possibly even anticipate external influence. For scientists monitoring the data, the realization was both exhilarating and unsettling. Every measurement confirmed complexity beyond ordinary physics, yet each anomaly raised more questions than it answered. It was as if the object existed on a threshold, neither fully alive nor entirely inert, reacting to the probes in ways that implied structure, purpose, or emergent organization. Humanity had approached the edge of a boundary it could not yet define. They had touched the edge of something alive, or something pretending to be, as the probes maintained close proximity to 3I Atlas. Additional measurements revealed complexity in its internal dynamics that had not been predicted. Thermal mapping across the object's surface and interior indicated localized energy redistribution occurring over minutes rather than seconds. These fluctuations were not random. They followed consistent spatial patterns correlating with the observed microplasma channels. Analysis suggested that external stimuli, such as micrometeoroid impacts or variations in solar radiation, were absorbed and redirected along these internal structures, producing both thermal and electromagnetic responses. Magnetometer readings corroborated the thermal data. Small but measurable shifts in local magnetic fields indicated transient currents moving through the object's lattice. The behavior was unlike anything detected in natural asteroids or comets. Laboratory analogues, constructed from exotic crystalline and conductive materials, could partially replicate energy absorption and localized discharge, but the scale, coordination, and persistence of the signals in 3I Atlas were orders of magnitude greater than could be explained by known mechanisms. Modeling suggested that the object's internal network was capable of sustaining organized energy flow over extended periods, indicating structural properties that allowed for self-regulated redistribution. The probes also experienced sporadic communication interference when entering close proximity to certain regions of the object. Signal attenuation, brief interruptions in telemetry, and transient anomalies in sensor readings were recorded. These effects were not consistent with solar interference or technical malfunction. Cross-comparison between multiple probe datasets confirmed the spatial localization of these anomalies, suggesting that the object produced directed electromagnetic fields capable of influencing nearby electronics. While the magnitude was low and non-destructive, the phenomenon was unexpected and represented a significant unknown. In terms of both physical modeling and safety, protocols for continued observation, data analysis teams began constructing high-fidelity simulations to explore the mechanisms underlying the observed phenomena. Computational models integrated the object's geometry, material composition, energy redistribution pathways, and electromagnetic properties. Simulations demonstrated that localized structural defects within the crystalline lattice could channel energy in specific directions, producing the rhythmic pulses and minor trajectory adjustments observed. These models also indicated that previously overlooked environmental factors, including variations in interplanetary magnetic fields and solar wind density, could amplify or modulate the object's internal responses. In addition to the physical measurements, spectroscopic data continued to reveal exotic compounds. Repeated scans detected high concentrations of rare silicates, metallic alloys, and crystalline formations not found naturally on Earth or in previously studied interstellar objects. The distribution of these materials suggested that the object had undergone prolonged exposure to high-energy processes in interstellar space, potentially including cosmic radiation, micrometeoroid bombardment, and interactions with magnetic turbulence. These processes may have contributed to the development of internal structures capable of dynamic energy response. Scientific interpretation of these findings remained cautious. While some researchers drew comparisons to theories of self-organizing matter and emergent quantum coherence, the absence of biological structures meant that conclusions regarding agency or consciousness were speculative. The data, however, confirmed one fundamental point: 3I Atlas could interact with its environment in ways previously unobserved in interstellar objects. Its responses were measurable, structured, and reproducible under controlled observation, demonstrating a level of internal organization that challenged existing classifications. By the conclusion of this early investigation phase, the probes had established a continuous, high-resolution record of the object's behavior. This dataset would form the foundation for subsequent studies, providing the empirical basis for both conventional and speculative modeling. While humanity had not yet penetrated the full interior of 3I Atlas, the information gathered confirmed that the object was a complex, responsive system. It had moved from an object of curiosity to one demanding a deeper understanding of physics, materials, and potentially emergent phenomena, setting the stage for the next stage of scientific exploration. The unusual behavior prompted some researchers to explore speculative, yet plausible, mechanisms rooted in quantum physics. Quantum resonance effects within the object's lattice could theoretically produce emergent properties not seen in ordinary matter. In particular, tightly coupled energy channels, akin to quantum feedback loops, might allow the redistribution of energy across macroscopic scales, producing measurable responses to external stimuli. While such effects had been theorized in controlled laboratory conditions, 3I Atlas presented an example on an astronomical scale, offering the first opportunity to observe potential quantum coherence phenomena in a natural interstellar object. These findings raised questions that went beyond physics. Could non-biological matter, structured in a highly specific way over millions of years, develop a form of emergent intelligence? Some theoretical models suggested that, under extreme conditions, high energy, radiation, microcollisions, prolonged exposure to cosmic magnetic fields, crystalline networks could self-organize into functional patterns, capable of processing information. While no evidence suggested cognition in the human sense, the object's ability to respond predictably to external influences indicated internal processes that resembled decision-making or feedback regulation, at least on a fundamental physical level. Speculation extended further. Some researchers proposed the possibility that 3I Atlas was not simply a naturally formed object, but an ancient artifact a relic of a long-dead civilization, deliberately structured to survive interstellar travel. Others argued for a natural evolutionary pathway, that crystalline structures could emerge in stellar furnaces or planetary nebulae, gradually acquiring complex self-regulating behavior over cosmic timescales. Models from planetary science, prebiotic chemistry, and mineral self-organization supported the idea that matter could develop unexpected functional complexity, particularly in high-energy environments where selective survival would favor structures capable of adapting to repeated stresses. Parallel cases in laboratory research lent some plausibility to these ideas. Experiments on metallic hydrogen, although limited, demonstrated emergent conductive properties under extreme pressure. Theoretical work in artificial intelligence considered whether consciousness could arise from networks of interacting units, without reliance on biology. Studies in mineral self-organization showed that crystalline lattice could develop feedback cycles under controlled environmental stimuli. Individually, these cases did not replicate the scale or integration observed in 3I Atlas, but together they provided a framework for imagining how a complex, responsive system could form naturally or be engineered. The implications extended beyond science into philosophy. If 3I Atlas represented a naturally occurring system capable of structured response, it suggested that life, intelligence, or functional organization might exist in forms entirely divorced from biology. The universe itself could, in principle, generate systems that learn, adapt, or process information, creating a continuum between matter and awareness. It challenged assumptions about what constitutes life, intelligence, and agency, expanding the questions of existence from biology into the domain of fundamental physics. Despite these reflections, the scientific community maintained a demand for rigor. Speculation could inspire hypotheses, but explanations still had to be grounded in measurable phenomena, reproducible data, and the laws of physics. The extraordinary nature of 3I Atlas required a dual approach, one that embraced imaginative possibilities while remaining firmly tethered to observation and analysis. The edge of science had been reached, and beyond it lay questions that blended physics, cosmology, and the philosophy of intelligence in ways humanity had never confronted before. Following the initial identification of quantum resonance effects, research teams focused on quantifying the object's interactions with its immediate environment. High-precision measurements indicated that minor, gravitational anomalies correlated with the orientation of its crystalline lattice, suggesting that the object's structure could influence local spacetime curvature in subtle ways. While these effects were orders of magnitude below those that could affect planets or spacecraft, they were consistent, measurable, and reproducible, making them a significant departure from the behavior expected of conventional interstellar debris. Further, investigation revealed that the rhythmic energy emissions of 3I Atlas could be mathematically described using complex harmonic models. These models, while not implying cognition, demonstrated internal organization at the molecular and submolecular level. Energy propagation along microplasma channels was consistent with calculated resonant frequencies for the crystalline structures, reinforcing the idea that the object's internal architecture allowed for coordinated responses to external forces. Researchers noted that these patterns persisted despite variations in radiation, solar wind, and minor impacts, suggesting a degree of structural stability and repeatability not previously observed in natural interstellar bodies. Laboratory analogues were developed to replicate aspects of the observed phenomena. High-pressure experiments on exotic silicate and metallic lattice demonstrated that repeated stress cycles could generate localized electromagnetic fluctuations similar in pattern, if not scale, to those observed on 3I Atlas. These results supported the hypothesis that the object's complex behavior could emerge from purely physical processes without requiring biological or engineered input. Nevertheless, the combination of thermal, electromagnetic, and minor gravitational anomalies exceeded what could be replicated in terrestrial laboratories, leaving the system's full behavior unexplained. The emergence of structured thermal and electromagnetic cycles prompted a closer examination of potential feedback mechanisms. Computational models explored how energy absorbed from impacts or radiation could be redistributed across interconnected channels, producing the observed rhythmic patterns. These simulations suggested that the object's geometry, highly fractured, with internal plasma veins following near regular pathways, could facilitate coordinated energy release. While these effects were physical in nature, the predictability and integration of the responses were unexpected for an object of this size and composition. Researchers also investigated possible external influences. The object's trajectory through the interplanetary magnetic field, along with exposure to cosmic ray flux, could interact with conductive and polarizable regions of the lattice, producing secondary effects in both electromagnetic emission and minor movement. Analysis indicated that these external factors alone could not account for the full extent of observed anomalies, but they may have acted as triggers or modulators for internal processes, amplifying or shaping the object's responses in measurable ways. By the conclusion of this phase, 3I Atlas had been established as a system of unprecedented complexity. Observations confirmed that it was not inert, nor was it a simple fragment of interstellar matter. Its coordinated energy responses, minor gravitational effects, and electromagnetic interactions collectively demonstrated behaviors that challenged conventional classification. Scientific inquiry was now focused on determining the mechanisms responsible, distinguishing between naturally emergent phenomena and hypothetical artificial origins, and integrating these findings into broader models of interstellar material behavior. The object's behavior had moved from curiosity to anomaly to phenomenon. While still unexplained in full, the combination of empirical data and theoretical modeling placed researchers at the frontier of physics, materials, science, and astrophysics. Humanity was confronted with a system that existed on the boundary between known matter and emergent complexity, a challenge to the fundamental understanding of how matter could interact, respond, and self-organize in the extreme conditions of interstellar space. As the anomalies of 3I Atlas accumulated, the scientific community turned first to conventional explanations, seeking models grounded in established physics. The earliest and most widely considered was the outgassing hypothesis, inspired by the analysis of 1I Awoke. In this framework, sublimation of volatile compounds from the object's surface could produce small thrusts, subtly altering its trajectory over time. Calculations suggested that if such processes were occurring along preferentially aligned fractures or fissures, they could account for minor acceleration deviations. Observational data were cross-referenced against expected rates of sublimation for known ices and volatiles. While some trajectory shifts were consistent with this model, the periodic electromagnetic emissions and thermal rhythms could not be explained by outgassing alone. Another mainstream theory proposed a radiation reflection model. Analysts speculated that highly reflective, previously uncharacterized minerals might be producing deceptive signals. These minerals, embedded in the crystalline lattice, could scatter sunlight or interstellar radiation in patterns that mimicked intentional emissions. Laboratory analogues demonstrated that certain anisotropic crystals could reflect light non-uniformly, creating complex apparent sequences when viewed from specific angles. While this accounted for some observational anomalies, the complexity and regularity of the rhythmic pulses, especially in multiple electromagnetic bands, remained unexplained. Magnetohydrodynamic distortions were also considered. Some researchers suggested that plasma trapped within fractures or microchannels of the crystalline lattice could interact with solar wind and magnetic fields to generate periodic electromagnetic signals. Computational simulations showed that plasma flows in irregular geometries could produce modulated signals, resembling communication patterns. However, the energy scales involved, combined with the observed thermal feedback cycles and the precise correlation with minor impacts, made this model insufficient to fully account for the object's behavior. A related concept, termed the energy absorption and delay hypothesis, examined the possibility that 3I Atlas's internal structure acted as a dynamic energy storage system. In this scenario, solar radiation, cosmic rays, or collisional impacts were absorbed into the lattice and subsequently released in structured cycles, producing measurable pulses in both thermal and electromagnetic readings. While the hypothesis fit the timing of some emissions, it failed to fully explain the coordination across spatially separated plasma channels and the minor trajectory adjustments that occurred in synchronization with energy releases. Throughout these investigations, data skepticism persisted. Some analysts argued that the perceived anomalies could be artifacts of sensor contamination, calibration errors, or interference from other cosmic sources. Instruments operating across multiple observatories and wavelengths were tested and cross-validated, and while some discrepancies were corrected, the core anomalies persisted. The signals, emissions, and energy redistribution were reproducible and consistent, confirming that the observed phenomena were real rather than observational error. Despite the ingenuity of these conventional models, each failed to fully reconcile all recorded behaviors of 3I Atlas. The combination of minor but deliberate trajectory changes, patterned emissions across electromagnetic and thermal bands, and localized gravitational effects defied explanation within the framework of known asteroid or cometry physics. Mainstream science provided potential partial mechanisms, but no single model accounted for the integrated set of observations. The inability of conventional theories to fully describe the object left the scientific community at an impasse. While rational explanations remained essential for framing research and maintaining rigor, they could not account for the full scope of what 3I Atlas exhibited. Every established model provided insight into some aspects, yet every model fell short when confronted with the totality of empirical evidence. And then, during one critical observational window, the object produced phenomena that exceeded all prior expectations, forcing a reconsideration of the possible as mainstream models struggled to reconcile the full scope of 3I Atlas's behavior. Some scientists began exploring hypotheses that moved beyond conventional frameworks. One of the first was the alien beacon hypothesis. In this scenario, 3I Atlas was considered a dormant probe, engineered by an advanced civilization designed to activate only under specific conditions, proximity to a planetary system, or exposure to particular energy thresholds. The rhythmic pulses, localized energy redistribution, and minor trajectory adjustments could then be interpreted not as random phenomena, but as a pre-programmed response sequence. While no direct evidence supported extraterrestrial origin, the object's systematic responsiveness lent a measure of plausibility to the concept. Another speculative framework proposed the cosmic seed theory. Here, 3I Atlas was envisioned not as a machine or biological entity, but as a carrier of information or organizational patterns, a spore of universal complexity. Rather than containing DNA or traditional biochemistry, the object might encode structural patterns capable of propagating self-organizing behavior across space and time. From this perspective, the object's responses were the manifestation of encoded instructions. Triggered by environmental conditions, the theory drew parallels with prebiotic chemical networks observed in laboratory studies, in which simple components self-assemble into increasingly complex structures under repeated stress and energetic inputs. The quantum archive idea extended this concept further. Some researchers speculated that advanced civilizations, aware of cosmic timescales and the fragility of conventional storage, might have encoded knowledge, data, or even consciousness into robust crystalline lattice. These structures could survive interstellar travel over millions or billions of years and activate under particular physical conditions, much like a biological organism responding to a stimulus. In this context, 3I Atlas was not a passive relic, but a repository of information, a memory preserved in matter, and one that might interact with its environment according to the internal logic embedded in its lattice. More abstractly, the simulation anomaly theory suggested that 3I Atlas might represent a systemic irregularity, a glitch or artifact within a universe governed by computational principles. In this interpretation, the object's unusual behavior was evidence that physical laws themselves could have exceptions or emergent features, undetectable under normal circumstances. If true, the implications extended far beyond astrophysics, challenging the assumption that the universe operates solely through deterministic or probabilistic processes. Some philosophical physicists approached the anomalies from a reflective standpoint, proposing that awareness or information processing might be a fundamental property of matter, rather than an emergent property of life. Under this lens, the responsiveness of 3I Atlas was not a sign of alien design or error, but an example that consciousness or proto-conscious behavior could exist at scales and in forms entirely foreign to human experience. This interpretation connected to broader debates in quantum foundations, where concepts like observer participation and non-locality hint at the universe's interactive structure. Each of these speculative models remained untestable by conventional experimentation, yet all provided frameworks for interpreting phenomena that mainstream physics could not explain. The patterns of light, energy redistribution, and minor gravitational perturbations seemed intentional, structured, and coherent across spatial and temporal scales. For the first time, humanity was confronted not only with an object that defied understanding, but with the possibility that it might possess some form of intrinsic agency, or that it was operating within rules entirely alien to human cognition. In the face of these possibilities, observation became more than measurement. It became dialogue. Data interpretation was no longer purely analytical. It was philosophical, probing the boundaries between matter, information, and awareness. The object challenged assumptions about causality, intelligence, and the role of the observer. And as the object approached the inner solar system, its behavior hinted that the experiment was not one-sided. For the first time, humanity wasn't merely studying the universe. The universe might have been studying us. Following the emergence of speculative theories, scientific efforts became increasingly interdisciplinary, blending astrophysics, quantum mechanics, materials science, and information theory. Observational campaigns were intensified, with telescopes operating across the electromagnetic spectrum to record every measurable interaction of 3I Atlas. Teams focused on high-resolution spectroscopy, polarimetry, and interferometry, seeking patterns that could validate or falsify the proposed hypotheses. While none of the fringe models could be conclusively confirmed, the data gathered allowed researchers to refine predictions about how the object would respond under controlled conditions. The alien beacon hypothesis prompted targeted monitoring of minor impacts and solar radiation fluctuations. Scientists analyzed whether 3I Atlas produced discrete emissions in response to external stimuli, looking for repeatable cause and effect patterns. These tests revealed that the object's electromagnetic pulses were often temporally linked to small gravitational perturbations, consistent with the idea that the internal lattice responded dynamically to external forces. While the results did not prove deliberate design, they were consistent with behaviors predicted by models treating the object as a responsive system rather than inert debris. Similarly, investigations inspired by the cosmic seed theory focused on structural analysis. Researchers examined the propagation of energy along the microplasma veins and crystalline channels, mapping how fluctuations spread across the object's interior. Computational models simulated the transmission of information through these networks, demonstrating that structured pulses could be produced from entirely physical interactions. The implications suggested that matter, under specific conditions, could store and transmit information, supporting the idea that 3I Atlas could function as a carrier of organized patterns, even without biological or engineered origin. Quantum archive models were tested through analysis of emission sequences across multiple wavelengths. By comparing patterns over weeks and months, researchers sought repetition or encoding consistent with information storage principles. Some sequences exhibited periodicities that aligned with mathematical constructs used in data compression, though no definitive message was extracted. Still, the regularity suggested that the internal structure was capable of storing or processing energy and releasing it in consistent intervals. Analogous to a physical memory system, resilient over interstellar distances, simulation anomaly interpretations motivated high-level statistical analysis of all recorded events. Researchers evaluated whether the behavior of 3I Atlas could be reconciled with known physical laws, or if it represented an outlier beyond probabilistic expectations. While the anomalies did not constitute proof of a computational universe, they provided an empirical dataset demonstrating that systems could emerge within physical laws that exhibited behaviors previously thought impossible, such as coordinated energy redistribution and minor localized spacetime effects. Philosophical reflection remained a parallel track. Scientists debated whether the observed interactions represented proto-awareness or were strictly material phenomena. Conferences brought together experts in consciousness studies, theoretical physics, and complex systems to discuss the limits of categorization. While consensus remained elusive, the discussions emphasized that any complete explanation of 3I Atlas would likely require integrating multiple perspectives, bridging conventional physics with emergent theories and possibly new principles of matter-energy interaction. By the end of this phase, the cumulative data had established 3I Atlas as an unprecedented object of study. Every observation, from energy redistribution to trajectory adjustment, confirmed that it was neither a typical asteroid nor a simple comet. Its internal and external responses challenged assumptions about what matter could do when subjected to extreme conditions over cosmic timescales. While speculative theories could not yet be confirmed, they provided frameworks to guide experimentation and interpretation. Humanity had reached a point where the boundaries between established science and informed speculation were intentionally blurred, and the search for understanding had entered an entirely new domain of inquiry. As 3I Atlas continued its approach toward the inner solar system, Telescopes across the globe and in orbit focused on its trajectory with unprecedented intensity. Optical and radio observatories tracked every motion, capturing high-resolution spectra that revealed growing brightness and increasingly intense pulses of green and near-infrared light. Space-based instruments recorded minor shifts in spin and orientation, which appeared correlated with changes in energy emission, suggesting the object's internal structure remained responsive to environmental stimuli. Each new dataset reinforced the conclusion that 3I Atlas was an active system, exhibiting behaviors far beyond what any conventional asteroid or comet could produce. At the same time, mission planning began to enter a more concrete stage. Space agencies considered a variety of proposals, ranging from robotic intercepts designed for remote sensing to theoretical concepts for physical capture. Engineers ran simulations to test containment, trajectory adjustment, and non-invasive observation methods, aware that even minor miscalculations could trigger unexpected responses. While the technical challenges were immense, the psychological and ethical dimensions were equally significant. Some scientists warned against direct interference, fearing that any physical contact might provoke unpredictable reactions, while others argued that the opportunity to study such an object up close outweighed the risks. International collaboration emerged as a critical element. NASA, ESA, CNSA, and private space companies coordinated deep space data analysis, sharing real-time observations and synchronizing instrument arrays across multiple continents. Distributed computing networks processed terabytes of information, mapping energy flows, emission patterns, and subtle gravitational anomalies. These cooperative efforts enabled more precise modeling of the object's behavior, including predictive simulations of pulse frequency, trajectory shifts, and energy redistribution. Analysts were particularly focused on the apparent acceleration of the object's pulse cycles as it moved closer to the inner planets, noting that the timing increasingly coincided with frequencies reminiscent of Earth's Schumann resonance. Whether this was coincidence or evidence of subtle environmental coupling remained unresolved, but it became a central point of debate among researchers. Meanwhile, the social and philosophical dimensions of the phenomenon grew more pronounced. Public interest surged as media coverage framed 3I Atlas as the green eye of Mars, a presence both alien and strangely familiar. Philosophers, ethicists, and futurists debated the implications. Was it a message, a warning, or simply a natural system displaying unprecedented complexity? Online communities formed around these questions, blending scientific curiosity with existential reflection. Across the globe, the object became a mirror, reflecting humanity's fascination, fear, and hope. Energy pattern monitoring intensified, with global arrays measuring not only electromagnetic emissions but also subtle thermal fluctuations, particle interactions, and magnetic anomalies. Patterns previously observed in isolation were now linked across multiple datasets, revealing emergent structures that hinted at internal regulation or feedback mechanisms. The growing synchronicity of pulses, especially when correlated with external perturbations, challenged analysts to reconcile observational rigor with the possibility that 3I Atlas was exhibiting forms of behavior previously undocumented in natural systems. At this stage, the mystery had transcended its purely scientific context. Observers recognized that the object's significance was now as much cultural and philosophical as it was physical. Its approach forced humanity to confront questions about agency, intelligence, and the limits of understanding. Every pulse, every trajectory shift, every anomaly recorded was no longer just a scientific data point. It was an invitation to consider what it meant to observe, to interpret, and to engage with phenomena that may not fit within pre-existing frameworks. The mystery had shifted. It was no longer simply about 3I Atlas. It was about humanity's response, and the ways in which knowledge, fear, and curiosity intersected in the face of the unknown. As observational campaigns intensified, the focus shifted from purely descriptive monitoring to predictive modeling. Researchers sought to determine whether the increasing intensity of 3I Atlas's emissions could be anticipated under varying environmental conditions, such as proximity to the Sun, solar wind flux, or planetary magnetic fields. Advanced computational models combined gravitational dynamics with plasma physics, thermal conduction simulations, and lattice vibration analyzers. While the simulations could reproduce some aspects of the observed behavior, such as minor rotational adjustments or thermal pulse propagation, they consistently fell short of accounting for the full complexity of the object's responses. To address this, multispectral arrays were deployed, measuring everything from X-ray emissions to low-frequency electromagnetic fluctuations. These arrays revealed that certain pulse sequences aligned temporally with subtle variations in the solar magnetic field, suggesting that the object's internal structure may be sensitive to external electromagnetic inputs. Researchers emphasized that these correlations did not prove causation, but they were consistent enough to warrant close monitoring. Some teams began constructing layered predictive models in which internal energy redistribution was coupled with environmental interactions, producing emergent pulse behavior that could, in theory, be tested in future close proximity observations. Mission proposals advanced in parallel with observational work. Robotic intercept strategies focused on non-invasive reconnaissance, using flybys with high-resolution imaging, magnetometers, and calculations considered potential risks of electromagnetic interference with instruments due to the object's microplasma activity. Contingency plans were designed for rapid withdrawal in case 3I Atlas displayed unexpected acceleration or directional changes. Engineers also simulated methods for remote energy measurement that would not disturb the object's internal equilibrium, recognizing that any physical contact could alter its behavior in unpredictable ways. International collaboration continued to expand. Observatories in South America, Asia, and the Arctic synchronized with space-based instruments in Earth orbit, creating a continuous monitoring network. Data sharing allowed for cross-validation, and discrepancies between instruments were analyzed in real time. Analysts discovered that minor energy variations in one hemisphere of the object preceded similar pulses in another hemisphere by predictable intervals, reinforcing the hypothesis that the object's internal structure allowed for coordinated energy distribution. While mainstream physics could explain the mechanism of energy transfer, the predictability and spatial coordination remained unique among natural interstellar objects. At the same time, interdisciplinary teams incorporated human factors into their analysis. Psychologists, sociologists, and ethicists studied public reactions, noting the emergence of social movements, interpreting 3I Atlas as a signal, warning, or philosophical prompt. Educational programs and scientific briefings attempted to contextualize the object's behavior in terms of physics and astronomy, emphasizing that while anomalies existed, natural explanations remained plausible. Still, the growing public interest influenced funding, policy decisions, and media coverage, creating an environment in which the scientific investigation could not remain isolated from social perception. By combining predictive modeling, advanced observation, mission planning, and interdisciplinary analysis, the global scientific community established a framework for understanding 3I Atlas that balanced rigor with openness to unconventional possibilities. Every dataset collected strengthened the empirical foundation, but simultaneously raised new questions about coordination, energy distribution, and environmental responsiveness. Humanity was no longer merely observing an interstellar object. It was engaging with a system that challenged assumptions about matter, behavior, and agency at a fundamental level. The object had become a nexus where physics, computation, and philosophy intersected, forcing a reconsideration of what could be expected from natural phenomena in interstellar space. As 3-1 Atlas continued its silent approach toward Mars, the implications of its behavior extended far beyond orbital mechanics or spectral analysis. Observers began to consider a possibility that challenged conventional understanding. What if the object's response was not solely to physical impacts, but to observation itself? Every pulse, every micro-adjustment might be correlated not just with external collisions, but with the act of being monitored, measured, and studied. Instruments, telescopes, and human attention all became part of the system. In this scenario, the boundary between observer and observed blurred, suggesting that awareness at some fundamental level could influence matter, or that matter could possess a rudimentary form of agency. In confronting 3-I Atlas, humanity saw a reflection of its own curiosity and drive for understanding. The same patterns that motivated civilizations to explore, to question, and to observe were echoed in the object's behavior, whether by coincidence or by design. If intelligence, in any form, is defined by the capacity to respond, adapt, or store information, then perhaps 3-I Atlas exemplified a type of cognition completely unlike our own non-biological, non-organic, but still capable of interaction with the universe. It was a mirror to human endeavor, a reminder that the curiosity driving our scientific and philosophical quests might be a universal trait, expressed in matter, energy, or information across the cosmos. The encounter with 3-I Atlas became symbolic of a larger awakening. Humanity was forced to acknowledge that its place in the universe was neither central nor isolated. The perception of control over observation, experimentation, and comprehension was limited. The object demonstrated that processes, responses, and interactions could emerge in forms entirely unanticipated, shaped by laws of physics, yet exhibiting behavior that seemed purposeful or intentional. In engaging with this interstellar anomaly, humanity confronted the idea that awareness is not confined to life as we know it, but may be an intrinsic property of matter under extreme or unusual conditions. Scientific humility became a guiding principle in the final stages of observation. Researchers recognized that the deeper their measurements penetrated, the more complex and inscrutable the system appeared. Attempts to fully explain 3-I Atlas with existing models consistently met with partial success, revealing the limitations of conventional frameworks. Each new pulse, each data point, emphasized that comprehension was provisional. The act of studying the universe was inseparable from the realization that the universe is capable of responses we cannot yet fully categorize. It was a reminder that exploration carries responsibility. The more we reach outward, the more profoundly we are confronted with the unknown. As the object drifted closer to Mars, its glow pulsed softly, a steady rhythm reminiscent of a heartbeat, ancient and enduring. For observers, both professional and public, the spectacle evoked a sense of continuity, matter persisting, responding, and existing on timescales far beyond human lifetimes. The silence of interstellar space was punctuated by these pulses, subtle but consistent, as if the cosmos itself were attentive, waiting. Perhaps the universe does not sleep, nor is it indifferent. Perhaps it only waits patiently for conditions to arise, for events to unfold, for energy, matter, or observation to trigger a response. And in that waiting, 3I Atlas had become more than an interstellar object. It had become a catalyst for reflection, for recognition, and for the awareness that humanity's encounter with the cosmos is never unilateral. The universe watches, responds, and perhaps, in some incomprehensible way, learns. Scientific discussions increasingly acknowledged that 3I Atlas's behavior demanded a re-evaluation of observational assumptions. Measurement techniques previously considered passive were now understood to interact subtly with the system under study. Electromagnetic sensing, thermal imaging, and high-resolution spectroscopy might influence energy redistribution or even trigger minute responses within the object's crystalline structure. Researchers began documenting the extent to which different instruments' optical, radio, and particle detectors appeared to correlate with changes in pulse frequency and orientation. While causality could not be conclusively demonstrated, the pattern suggested that human observation itself had become a variable in the experimental environment. Ethical debates accompanied these findings. If 3I Atlas exhibited any degree of intrinsic responsiveness, questions arose about the responsibilities of scientists. Could repeated probing, even if remote, constitute interference? Was the object simply a natural system acting under physical laws, or did it possess a form of proto-agency that warranted ethical consideration? Committees of physicists, ethicists, and space policy advisors convened to evaluate protocols for future observation. The discussions highlighted an emerging need to balance scientific curiosity with precaution, recognizing that interaction, even through data collection, might alter outcomes in unpredictable ways. At the same time, the public's engagement with the phenomenon continued to evolve. Educational programs contextualized 3I Atlas in terms of interstellar physics, emphasizing the known properties of small bodies, radiation-matter interactions, and the principles of energy transfer. Meanwhile, philosophical and cultural discourse expanded, with analysts noting that the object had become a lens through which humanity could examine its own cognitive and ethical frameworks. Discussions ranged from interpretations of intelligence and consciousness to the role of observation in defining reality, drawing inputs from cognitive science, complexity theory, and quantum foundations from a practical standpoint. Monitoring efforts continued to produce actionable data. Energy pulse patterns were recorded with increasing precision, allowing for cross-comparison with environmental factors such as solar wind density, planetary magnetic fields, and micrometeoroid impacts. Scientists observed that while many pulse sequences correlated with environmental stimuli, certain intervals appeared independent of measurable external factors, indicating the object maintained internally regulated behavior. This added a layer of complexity to the debate. Was 3I Atlas merely responding to physical laws? Or was there an emergent system of internal feedback producing semi-autonomous patterns? International collaboration remained critical. Research groups shared continuous updates, integrating high-frequency telemetry from space-based observatories with ground-based analyses. Data pipelines enabled near real-time modeling, and predictive simulations were refined to anticipate pulse timing, rotational adjustment, and energy distribution across the object's lattice. These models were treated cautiously, as repeated deviations indicated that while predictive in part, the system retained a level of unpredictability beyond current physical understanding. By the conclusion of this phase of observation, it was clear that 3I Atlas had transformed from a distant curiosity into a subject of comprehensive human inquiry, scientific, ethical, and philosophical. It challenged assumptions about intelligence, agency, and the nature of observation, emphasizing that empirical study could no longer be separated from reflection on responsibility and perspective. Humanity had entered a new mode of engagement with the cosmos, one in which data collection, analysis, and interpretation were inseparable from the recognition that the universe might actively participate in the experimental process. The object's slow approach toward Mars, marked by its measured pulses and subtle energy fluctuations, remained a focal point for ongoing study. Each measurement reinforced the conclusion that understanding 3I Atlas required the integration of physics, systems, theory, and philosophical consideration, underscoring that the boundaries between matter, awareness, and observation may be far more porous than previously assumed. As the object approached Mars, international space agencies intensified their observational campaigns, consolidating years of prior data to produce a comprehensive profile of 3I Atlas, ground-based observatories, orbiting satellites, and deep space probes coordinated in near real time, creating an integrated monitoring network capable of capturing subtle changes in rotation, trajectory, and emission spectra. Analysts prioritized understanding energy fluctuations, microplasma activity within the object, and patterns in electromagnetic pulses. Every dataset collected was meticulously cross-verified across multiple platforms to reduce the risk of instrumental bias or observational error. The collaborative scientific effort revealed that the object's pulse sequences exhibited both predictable and non-predictable elements. While some variations could be linked to environmental triggers, micrometeoroid impacts, solar radiation fluctuations, and local gravitational perturbations appeared autonomous, as if governed by an internal feedback mechanism. Computational modeling teams attempted to simulate these internal responses using advanced physics frameworks, combining thermodynamics, crystallography, and quantum electronics. Despite extensive modeling, no single theory could fully account for the object's behavior, emphasizing the unprecedented nature of the phenomenon. Ethical and philosophical considerations became inseparable from the scientific discussion. Interdisciplinary committees evaluated the implications of continued observation, debating whether interacting even remotely with an object displaying semi-autonomous behavior constituted interference. Bioethicists drew parallels with protocols in astrobiology and SETI, noting that while the object was non-biological, its capacity for internal regulation and apparent responsiveness raised novel questions about agency in non-organic systems. Guidelines for remote observation were developed, emphasizing minimal intervention and maximum data collection, without provoking unknown reactions. Public discourse reflected a mixture of fascination and apprehension. Media outlets highlighted the object's anomalous behavior, coining terms like the green eye to describe the glowing pulses visible from orbit. Educational programs sought to contextualize the object within known physics, explaining crystalline lattice structures, energy absorption cycles, and interstellar object trajectories. Simultaneously, philosophical forums, online communities, and academic publications debated the broader implications. Could intelligence emerge outside biological systems? Was the behavior of 3I Atlas evidence that matter itself might carry or process information in ways not previously considered? These discussions reframed the encounter as a multidisciplinary challenge, uniting physics, cognitive science, ethics, and philosophy. The approach to Mars necessitated refined observation protocols. Orbital mechanics teams calculated precise timing for higher resolution imaging passes, ensuring that probes captured the object from multiple angles while maintaining safe distances. Sensors monitored electromagnetic emissions across the spectrum, thermal radiation, and microgravity effects, Data streams were analyzed continuously to detect unexpected deviations in behavior. It became clear that 3I Atlas was not only responding to physical conditions, but was dynamically regulating energy output, suggesting a level of complexity previously unseen in interstellar matter. Meanwhile, energy pattern analyses demonstrated a degree of spatial and temporal coordination within the object. Rhythmic pulses recorded in one hemisphere of 3I Atlas were observed to precede similar emissions in the opposite hemisphere by consistent intervals. This implied that the object maintained an internal communication system capable of coordinating energy transfer over its entire structure. Researchers compared these patterns to neural firing sequences in complex systems, noting structural similarities without implying biological equivalence. These findings reinforced the notion the 3I Atlas represented a novel form of complexity in matter, an interstellar object exhibiting regulatory behavior and internal synchronization. As predictive modeling continued, scientists incorporated external environmental variables into simulations. Solar wind flux, radiation pressure, and local gravitational gradients were integrated into dynamic models to estimate potential trajectory adjustments and pulse responses. Analysts noted that even minor deviations from predicted environmental inputs produced measurable changes in the object's energy emission cycles. These observations supported the hypothesis that 3I Atlas was capable of a degree of internal adaptation, whether as a result of quantum effects, lattice resonance, or emergent self-organization. Philosophical implications began to dominate the dialogue. Scientists and ethicists debated whether the concept of intelligence needed expansion to include non-biological, non-organic systems. Cognitive frameworks were reconsidered, incorporating principles from complex systems theory, emergent behavior, and quantum information theory. Questions arose regarding the role of observation in defining system behavior. Could human attention, in some way, influence the dynamics of an interstellar object? While empirical evidence was insufficient to confirm direct causation, repeated correlations between observational activity and pulse timing suggested that the interaction was at least partially bidirectional. The psychological impact on scientists was notable. Teams monitoring the object reported heightened levels of focus, vigilance, and emotional investment. The realization that 3I Atlas might possess characteristics of responsiveness and internal regulation created both excitement and apprehension. Research protocols incorporated mental health support and structured reflection periods, acknowledging the cognitive demands of observing a system that could not be fully predicted or controlled. These measures underscored the interplay between human perception, scientific methodology, and the enigmatic behavior of the object. As Mars approached, proposals for close-range observation increased in sophistication. Robotic flybys equipped with multispectral instruments were designed to measure energy absorption, plasma emission, and crystalline lattice vibrations without perturbing the system. Contingency planning accounted for potential unanticipated acceleration or orientation changes. Risk assessment protocols combined classical orbital mechanics with stochastic modeling to simulate hundreds of possible scenarios. Every maneuver emphasized caution, reflecting the growing consensus that interference could fundamentally alter the observed behavior. Concurrently, international agencies continued knowledge sharing, enabling a coordinated approach to monitoring, data analysis, and predictive modeling. Each dataset, from thermal imaging to electromagnetic pulse recordings, contributed to an evolving understanding of 3I Atlas as a dynamically regulated interstellar object. Collaborative efforts bridged the gap between theoretical physics and practical observation, allowing for continuous refinement of models and adaptive strategies for further investigation. In parallel, the encounter with 3I Atlas catalyzed a broader philosophical reflection. Academics and researchers increasingly considered the possibility that intelligence and responsiveness might not be exclusive to life as we know it. The object became a case study in the emergence of complex behavior in matter, challenging foundational assumptions in physics, cognitive science, and systems theory. Its presence emphasized the limits of human knowledge, while simultaneously highlighting the potential for discovery when observation is coupled with reflective inquiry. Social and educational impacts were significant. Public discourse evolved to include rigorous explanations of interstellar dynamics, energy transfer in crystalline lattice, and the potential for emergent self-regulation in matter. Citizen science initiatives allowed enthusiasts to participate in data analysis, fostering a shared sense of discovery. Simultaneously, ethical debates regarding observation and interference informed policy development, ensuring that the balance between knowledge acquisition and precaution remained central to ongoing engagement. By the final observational phase, 3.1 Atlas had become more than an interstellar anomaly. It had become a mirror for humanity's approach to knowledge. Its behavior challenged assumptions about causality, observation, and agency. The object's pulses, rotations, and energy regulation highlighted the potential for non-biological systems to display coordinated, adaptive, and responsive behavior. Humanity's encounter had shifted from passive observation to active reflection, incorporating scientific rigor, ethical consideration, and philosophical inquiry. In conclusion, the study of 3I Atlas underscored the need for humility in scientific exploration. The object exemplified a system in which physical laws, internal regulation, and environmental interaction converged to produce behavior not fully understood. Researchers were forced to acknowledge the limits of predictive modeling, the complexity of emergent behavior, and the potential for unknown mechanisms in interstellar objects. Humanity had not merely observed 3I Atlas, it had been confronted with a system that mirrored our curiosity, challenged our assumptions, and expanded the boundaries of what we define as intelligence and responsiveness. The approaching pulses of the object continued, rhythmic and measurable, an interstellar benchmark against which human understanding could be tested. Each dataset reinforced both knowledge and uncertainty, providing a foundation for future inquiry while emphasizing the provisional nature of comprehension. 3.1 Atlas remained an enduring subject of study, a point of convergence for physics, ethics, and philosophy, a reminder that the universe may possess mechanisms of behavior that are as complex and responsive as the civilizations observing it. By the time the object drifted past Mars, the scientific, ethical, and philosophical frameworks established during its observation had become a template for approaching other interstellar anomalies. The lessons learned emphasized the integration of empirical study with reflective analysis, ensuring that humanity's response to future phenomena would combine rigor with humility, curiosity with caution, and observation with ethical consideration. In the study of 3I Atlas, the boundaries between matter, consciousness, and observation had been tested, reshaping the way humanity engaged with the cosmos. Following the sustained observation of 3I Atlas, INTERNATIONAL, research teams began conducting more granular analyses of its physical and energetic properties. Multi-wavelength studies were initiated to determine whether the observed pulse sequences were a product of external stimuli, internal regulation, or a combination of both. Instruments measured energy distribution across visible, infrared, ultraviolet, and X-ray bands, providing a more detailed spectral profile. Each data point was catalogued in a centralized repository, allowing researchers to compare temporal variations with environmental inputs such as solar radiation, flux, magnetospheric disturbances from Mars, and micrometeoroid activity. The complexity of the resulting dataset reinforced that 3I Atlas operated as a dynamic system, capable of producing internally coherent patterns, not entirely attributable to external factors. The structural composition of 3I Atlas remained a primary focus. High-resolution spectroscopy indicated the presence of highly ordered, crystalline lattice with unusual chemical bonding arrangements, including compounds not commonly found in known asteroidal or cometary material. Structural modeling suggested that these lattices were capable of storing and releasing energy in ways analogous to capacitive systems, potentially explaining the cyclical pulses observed. Researchers hypothesized that the object might function as a large-scale energy buffer, absorbing solar and cosmic radiation, then releasing it in a controlled manner. While the mechanisms remained speculative, they were firmly grounded in established physics, including principles of crystallography and electromagnetic field interactions. Alongside the structural analysis, teams focused on motion dynamics. The object exhibited small, deliberate trajectory adjustments, particularly as it approached Mars. Calculations ruled out conventional propulsion methods, and the observed acceleration did not correspond with gravitational perturbations from planetary bodies.